Exploring optical biosensors from basic principles to modern applications. What is a biosensor? Let's begin with the basic idea. A biosensor is a self-contained device that uses a biological recognition element in direct contact with a transducer to provide specific qualitative or semi-quantitative analytical information. In simple terms, it combines biology and electronics to detect something and convert that detection into a measurable signal. The first biosensor was developed in 1950 by L. Clark. It was used to measure oxygen in blood and became known as the Clark electrode. Later, enzymes such as glucose oxidase were added to measure blood sugar, and urease was used to detect NH4+ ions to calculate urea levels. Biosensors developed through 3 generations. In the first generation, the product of the reaction diffused to the sensor. In the second generation, mediators were introduced to improve the interaction between the reaction and the sensor. In the third generation, mediators were removed and the response directly initiated the reaction. Every biosensor has 3 main components: a bioreceptor, which specifically interacts with the analyte, a transducer, which converts that interaction into a measurable signal, and an electronic circuit or display, which processes and shows the result. Based on the type of transducer, biosensors are classified as electrochemical, physical, or optical. Today, we focus on optical biosensors. Why optical biosensors? Optical biosensors work through the interaction between light and the target analyte. When the analyte interacts with the biorecognition element, it changes the optical properties of the system. The transducer converts this change into an electrical signal. The signal is proportional to the concentration of the analyte. Optical biosensors are widely used because they offer high specificity and sensitivity. They allow real-time and continuous monitoring. They are small in size and cost-effective. These advantages make them useful in healthcare diagnostics, environmental monitoring, and food safety. How optical biosensors work. All optical biosensors are based on the interaction of light with biological materials. They detect changes in light properties. Specifically, they measure changes in intensity, wavelength, or phase of light after it interacts with the analyte. Biological molecules have unique optical characteristics. Even small changes in refractive index or molecular binding can change these light properties. By measuring these changes accurately, the biosensor can determine the presence and concentration of a target substance. Major categories of optical biosensors. Optical biosensors can be classified in different ways. Based on their mode of operation, they are either label-free or label-based. In label-free systems, the analyte directly interacts with the transducer to produce a signal. In label-based systems, a label, such as a fluorescent or colorimetric marker, produces the detectable signal. They can also be classified by design and detection mechanism. Major categories include surface plasmon resonance, or SPR, localized surface plasmon resonance, or LSPR, surface-enhanced Raman scattering, or SIRS, and optical waveguide-based sensors. These categories help us understand how different optical biosensors operate. Plasmon-based sensors, SPR and LSPR. One important optical biosensing technology is surface plasmon resonance, or SPR. SPR detects analytes by measuring changes in refractive index at a metal surface. When polarized light hits a thin metal film, it excites surface plasmons, which are collective oscillations of electrons. Under resonance conditions, this creates an evanescent field that extends into the nearby medium. If the analyte binds near the surface, it changes the local refractive index. This shift changes the resonance condition. It appears as a shift in the dip position in the reflected light spectrum. This shift allows us to measure analyte concentration. Localized surface plasmon resonance, or LSPR, is similar but uses metallic nanoparticles instead of thin films. In SPR, the electric field is confined to about 200 to 1,000 nanometers. In LSPR, it is confined to about 20 to 40 nanometers. Because of this stronger localization, LSPR offers higher sensitivity and selectivity compared to SPR. SIRS and luminescence. Another highly sensitive technique is surface-enhanced Raman scattering, or SIRS. In SIRS, molecules are placed near nanostructured metallic surfaces, such as gold or silver nanoparticles. When light excites surface plasmons at these nanostructures, the local electric field increases greatly. This leads to a strong enhancement of the Raman signal, about 10 to the 6th to 10 to the 8th times stronger than normal Raman scattering. There are two enhancement mechanisms: electromagnetic enhancement, caused by the amplified electric field, and chemical enhancement, caused by electron transfer between the molecule and the nanoparticle. Luminescence-based biosensors use light emission instead of scattering. These include fluorescence, chemoluminescence, and bioluminescence. In fluorescence, light is emitted at a specific wavelength after excitation. In chemoluminescence, a chemical reaction produces light. In bioluminescence, light is emitted from biochemical reactions inside living organisms. These systems are known for high sensitivity and selectivity. Waveguides, interferometers, and resonators. Optical biosensors also use waveguides, interferometers, and resonators. In interferometry-based sensors, a light beam is split into two paths, a sensing arm and a reference arm. If the refractive index in the sensing arm changes because of analyte binding, it creates a phase shift. When the two beams recombine, this phase shift produces an interference pattern. This pattern can be measured to determine analyte concentration. Waveguides confine light and use the evanescent field that extends into the surrounding medium to detect binding events. Resonator-based biosensors confine light inside a cavity where it interferes with itself and creates resonance. These systems are evaluated using parameters such as the Q factor. Recent advances include multimodal platforms that combine techniques like LSPR, SIRS, and fluorescence to improve sensitivity and detection limits. Optical fiber and real-world performance. Optical fiber-based sensors operate using total internal reflection. For total internal reflection to occur, the refractive index of the core must be greater than that of the cladding, and the incident angle must be greater than the critical angle. When light travels through the fiber, most of it stays inside the core, but the evanescent wave extends into the cladding region. If the cladding is modified with plasmonic materials, the evanescent wave can excite plasmons. Changes in the sensing medium then change the resonance condition, which allows analyte detection. Recent optical biosensors show detection limits ranging from picomolar to millimolar levels. These detection limits demonstrate that optical biosensors can achieve very high sensitivity in real applications. Challenges and future directions. Despite these advances, several challenges remain. Future optical biosensors aim to improve lab-on-a-chip technology to reduce sample volume and detection time. Reducing background noise is important because noise lowers signal strength and sensitivity. There is also a need for multitasking systems that can manage sample injection, mixing, reaction, and detection at the same time. Multiplexing detection is another goal. This allows multiple analytes to be detected simultaneously without interference. Integration with wearable and implantable systems requires biocompatibility